So hopefully none of you showed up on Thursday by mistake. I was in Baltimore having a lovely time there with all my colleagues. It was fun. By the way, the same conference that I went to, it's called SMEP, the Society for Multivariate Experimental Psychology. It's quantitative psychologists predominantly, but there's some folks in education. That conference is actually coming here next year. It's a closed meeting. You have to be invited to go, but people who are part of the local arrangements get to go for free. So if you're interested in hanging out with some quant nerds, right? What do you think, Jihong? You went? It was fun?
Pretty good. Yeah.
It's pretty good?
A lot.
Yeah.
Other pals and professors.
Yeah, and it's nice to be able to actually talk to the people in the field, like whose papers you read and whose books you have and stuff like that. So anyway, that's where I was. Here's where we are. We have a quiz to go over. So formative assessment, as I like to call it, just as a reminder, I don't grade for accuracy, just completeness and effort. So I set these up so that you can do multiple attempts. So if you'd like to log back in and start another attempt so that you could take notes for yourself, you'd be welcome to do that. That's fine. Or you can just, write it down however you'd like. So let me make this a little bigger here. So describe the difference between centering using a constant and group mean centering for level 1 predictors. So what's the difference? Well, the answer's sort of in the question. I'll give you that. So this is meant to be a softball to start you off, right? Centering using a constant and group mean centering. So centering using a constant is my more general way of saying grand mean centering. It doesn't have to be the grand mean, though, but the same principles hold no matter what constant it is. What's the difference between that and group mean centering? All right, I'm going to start calling on people. We'll be all Elizabeth Warren Socratic method here. Let's see. Kayla, I'm calling on you.
Yeah, are you looking for us to tell you that the within group variation, is that what you're looking for what I wrote was centering at the group mean allows us to compare a person relative to the rest of the group. This gives us within group variation level 1. If after centering the within group predictor is negative, then we know that person is lower compared to the rest of the group. If it's positive, then they can be higher. And then I also went on to say that we would subtract any number from the group based on comparability. The difference between this and the method above is that we're comparing groups instead of people. So I wasn't sure if you were looking for like within versus between. Explanation is longer, but that's the short version.
Yeah, no, I was looking for all of that. So the major sort of umbrella, the idea that group mean centering is centering at a variable. So you're subtracting a different number for every group based on their mean, whereas any kind of centering constant is just shifting it over. So you're changing the kind of variability the level 1 predictor has when you're doing group mean centering. You're not when you're doing grand mean centering. And so then, yes, the definition of what the variable means changes. Group mean centering means it's you relative to the average. So it's a relative phenomenon. Whereas centering with the constant, it's still you relative to some number, which is both group level information and individual level information. So yeah, all of that works for me. Yes. And then the what happens at level 2 then I think is a different one.
The same question, like what you were looking for too. So I kind of just rephrased it a little bit.
Yeah, that's so when using group mean centering for a level 1 predictor, how does one interpret its fixed effect? So yes. So you gave me that. Someone else say it in their own words. Or I start calling. All right, I'm going to call on Harry. You're looking for your answer? Do you want to phone a friend? Like throw it to someone else? Who? Okay, it's to you. How does one interpret the fixed effect of a level 1 group mean centered predictor? Kayla already said it in one way. I want you to say it in your way. See, and this right here is why I don't teach just once a week, right? Because a week between classes, it's like, oh my God, that was so long ago. Did I do this last week? Yeah. Do you want to phone a friend? Or want to give it a try?
Yeah, I'm trying to think, like, to phrase it in a different way than Caleb.
Well, you can say it in whatever way you want.
So it's so for the level 1 predictor, it's describing the change in the outcome variable when you are like relatively higher than your peers within the same group.
Yeah, I like that. It's the change in the outcome, your outcome, right? It's an individual level effect for you being relatively higher relative to the rest of your group. Yeah, I like that. And we know that that has to be that way because that's the only kind of variability a group mean centered predictor has. That's the key, is that by taking out the group mean, you have taken out the level 2 intercept variability. The only thing that's left is that relative to the group information. And so its resulting effect can only be that. So how does one then interpret the fixed effect for the level 2 group mean? We'll just keep moving down the row. Your turn.
So it's how your outcome variable will change if your group is higher than other groups.
Mm-hmm.
Yeah.
Yeah, so it's the effect of being from a group that is higher than other groups.
Yes.
And so it's the effect for the whole group.
Yes.
Like the whole group's outcome goes up because the whole group's X is higher than the rest.
Yeah.
So if you think of these as sort of like global local, like a level 2 effect is a global effect and a level 1 effect is a local effect. Like micro, macro would be another way of thinking about that. Good. And do these interpretations change if either predictor is not included, Elmira? I should say your name first, right? Then you get so do these interpretations change if either predictor is not included?
I remember that sometimes it changed, but sometimes it was exclusion.
That's the next specification. So under group mean centering. So you have taken the level 2 variability out of the level 1 predictor. Your level 2 group mean predictor only has level 2 variability. So do these interpretations change if either predictor is not included? Correct, it does not. What are we assuming about a predictor if we don't put it in? If we put in just level 1 or just level 2 under this method? Zero, yeah. It's just not, it doesn't have an effect, right? The same as not putting any other predictor in a model. That's always what we assume. It doesn't have an effect if it's not there. And that is why I like this way better. Number 3, now the other way. When using constant centering for a level 1 predictor, so just picking a constant to center to shoving it over, rescaling, how does one interpret its fixed effect when included by itself? All right, I'm calling on Molly, starting up the next row.
So I put that count individual compared to others in a group only after statistically controlled for predictor interest.
But if it's by itself, what does it mean before controlling for other stuff? So if there's no level 2 analog, if we put in a constant centered level 1 predictor, what does its effect mean? I think you answered a different question, is what I'm saying.
Okay.
Mm-hmm. So it still has both level 2 between group variance and level 1 within group variance. Therefore, its effect has to be both of them at once. And I call that, starts with an S, smushed. Other people call that, Convergence is one. From the conference, there were several talks about this. Conflated. Yeah, that's Chris Preacher's term, people at Vanderbilt's term, and UNC's term. I like smushed better. I'm trying to make it a thing. But yeah, the idea is that if you just put it in by itself, because it has two kinds of information, you are saying that both effects are the same. So it's always going to be a misspecification because that's not likely to be true conceptually or statistically, given that these are unstandardized coefficients on different scales. So then, how does this effect change after including the level 2 group mean? So Molly, I'm going to call on you on the last question again because that's the one you answered. So just give that thing. So I'm going to do the middle question here. How does this effect change after including the level 2 group mean? Shinji, it's you.
Then like our interpretation would be same as a conclusion too, like simply like within each school, like how much like why change, by the why increase x1.
Then it becomes the pure level 1 within effect because it's been statistically controlled for the group mean as opposed to just having the group mean subtracted from it. It's two different ways of accomplishing the same goal. Yes. And so, yeah.
I have a question. So, for the first part, like in level 1 predictor, like if we put itself, by itself,
Mm-hmm.
the coefficient actually we get on the like regression table will be the same as the like a coefficient from the just regular regression, like without like putting on the
Yes, regular regression, but the standard error won't be. But yes, and that's another reason why that would be wrong, right? Like the idea is that you're not considering the multi-level nature of the predictor or the outcome in that case. Yep. Okay, Molly, back to you. Okay, how does one then interpret the fixed effect of the level 2 group mean? Yes, indeed. And what does that mean?
It's after controlling for the individual the effect of.
Yes, it's the incremental effect of the group after controlling for the effect of the individual. Yes, that is what contextual means. Can you give me another definition? Let's see, Emily, your turn. Can you give me another definition of a contextual effect? I'll get you started. It's something minus something. And you can phone a friend too if you want. By the way, that for you young people, that's an expression from a game show. It was yeah, what is it called? Who Wants to Be a Millionaire? And you have to answer all these questions, and they give you lifelines, and one of them is phone a friend. So you're allowed to call somebody and have them answer the question for you. And I know that, we don't have phones, but we're all in the same room, so we don't need them. So would you like to phone a friend, Emily, or you want to give it a try? Okay, she's phoned Kofung, right?
Oh my god.
Well, to be fair, he's not registered for this class, so I don't have to, punish him, but would you like to answer it? It looks like you've got the right section. Other definition of a contextual effect, something minus something else.
Something minus something else.
Yeah.
I'm gonna use call out again.
You're gonna phone a friend?
Can I call Jiho?
Okay, Jihang, he's phoned you. Contextual effect is blank minus blank. That's the more mathematical definition. I'll give you a hint. I said it's the formula test of whether you're allowed to smush. We're running out of people to phone, but there's a few left who haven't been called on yet. There's a slide with algebra on it. Look at that one. He's like, I didn't bring my computer over. Shit. No? Okay. Wei? There it is. Ding, ding. It's the between minus within. So the contextual effect is either the difference of the between and withins. Equivalently, it is the incremental between after controlling for the effect of the individual. Yes. And all of that sounds all well and good, but how would this play out in something you care about? So several of you are not majoring in quant, you're majoring in other things, and even amongst the folks from the quant, you work with data and projects. So I expect that everybody should be able to come up with an example of some kind, right? Anyone want to play? Juliana, can I call on you for this?
Yeah, I'm thinking here. I've got to miss the last 2 classes, so.
She's like, I got a midterm this afternoon. Don't bother me right now. See, it could be worse, right? This could be a midterm. I know, right? Do you know why I don't believe in midterms or finals or tests, period? Because I never believe there's a situation in the rest of your professional life where you have to dump your brain without help as fast as possible and only be right that day, right? There is none. Everything else you prepare for, you know what the questions are going to be, you get a chance to fix it, right? Like think about submitting manuscripts. Do manuscripts get accepted on the first try? No, that's not a thing. I mean, I know like in theory it's a thing, but that is not a thing. Your best hope is that they don't reject it outright and they give you feedback as to why they hated it or what they didn't understand and you fix it, right? And then you get it. How about grants? Do you get a grant on the first try? Also not a thing. So they give you feedback about what they hated and what's wrong with it and you fix it and then maybe you get a grant. So the rest of your life learning from your mistakes is how you're going to put food on the table, right? That's why I don't give tests. But I digress. Can someone give me an example? You got one?
So I try to use the read, which is the number of books a student read.
Okay.
So, and then for the group mean century, level 1, maybe, as well as the school mean read included at level 2. Level 1, we have the reading group effect, so which means the effect of the kid with more books to read relative to the school.
Mm-hmm.
So probably for the kids, so can read more books because it's which family.
What's the outcome in my story here?
Of their performance, their just academic score or their overall
Okay, academic something.
something or their overall kind of ELA, so result.
Okay.
So and then level 2, which means that you have going to a school with more books available, both at school and at home, that's in a rich area or in a rich neighborhood. So there's more books to read. Grant means something like level 1 students read more. And as well as the school read included at level 2. So again, for level 1, we can be back within kids with more books to read relative to their school. It's purely within group after a statistic control for read for the group as well as the level 2. And that's the effect. So incremental effect of going to school with more books to read after a statistic control for the student. Something like that.
Yeah, that sounded great to me. So paraphrasing, since your voice won't pick up on the recording here, the example was how many books you have available to read on achievement of some kind. Students who have more books than others in their peer group, school, whatever it is, may have better outcomes for themselves. Schools that have more resources, more books and stuff, may have better outcomes than other schools. And it's possible that if you go to a good school, even after controlling for how many books you have, your school performance might be better, the school's performance. So yeah, I like it. Others? Anyone else want to play? Go for it.
Okay, so a student has a high ACT score relative to other students at their school. They're more likely to enroll in post-secondary education.
Yes?
Schools with higher average ACT scores relative to other schools have higher rates of college going.
Okay.
And then students who attend schools with higher average ACT scores are more likely to enroll in post-secondary than students enrolled at a high school with lower relative ACT scores after controlling for their own.
Yes, I love it. Absolutely. So the smarter you are relative to your peers, as supposedly measured by the ACT, or the more college ready you are, is that better? Yeah, I got to put the air quotes on it, right? Yes. The better you did on a test of questionable validity Should I say that out loud? Shit, I forgot who pays me. The better you do on a standardized measure, the more likely you are to attend college. The more people from your school who do well, more likely a higher college rate at the school. I like the changing of the phrases that you did there, much better than I did. And then going to a school with lots of kids who did well on the ACT helps your score incrementally even after controlling for how well you did. So the, what is it, all boat, what is that saying? All boats are, the tide, that, yes, the tides raise all boats. That's the contextual effect would be that, right? Like everyone around you enhances you even after how much you can help do for yourself. So yes, that's a good metaphor to end on, I think. So any questions on these? Yeah.
Is it possible for you to post the standardized the correct answer?
Uh,
Your hours is more local and then not standardized the correct answer, but this one is very kind of interesting and very important.
It is very interesting and very important. Let me see.
Yeah, because I feel our interpretation is more from our perspective, even though it's acceptable, but I don't think it's very, very accurate. It's kind of acceptable.
Well, Radenbush and Breck, I think, is probably the reading that I would go to with this. They have a good between contextual explanation. I was going to say my paper, where did I put my paper on here? I have a new paper that I really like. I put it down here because it's in multivariate, but the first half of it goes over this. So it's a tutorial on centering for the first half. So it's literally just like me transcribing what I would say in class into Word. So I would check out the first half of that as to everything that, and even one of the pictures I stole here is from that. So that will be more comprehensive than whatever I type as responses to this quiz. So, sure. All right, others. All right, then we have some new stuff to talk about then. We foreshadowed at the end of last week the idea that so far we've talked about fixed effects only. So the effect of being relatively more something on your performance. But it's possible that the effect of being relatively more something depends on the rest of the group. It may differ by group. So we're talking about adding potentially random effects for your level 1 predictors as well as cross-level interactions to explain them. So we're starting with lecture 3B. And while you're pulling that out, by the way, I wanted to apologize for homework 2. I don't know what the hell happens, but it's going to take, it was going to take more time than I had sitting at an airport to figure it out, why the coding went awry. So just know that I'm working on it and I will let you know once it's fixed. I had to get, the class before you guys didn't have a lecture for today. So they're the ones who got the airport time to figure this out. But I will work on it and I will fix it. Homework 3 is out. Are you guys working on that? Well, are the people who are supposed to be working on that, right? Not the auditors. So let me know if you have questions on that as you get through that. But that one should be based on example 3A up to section 4, and then sections 5 and 6 are covered in what we're going to talk about here. So that's due a week from tomorrow. So we talked about variance explained. Level 2 effects explain level 2 variance. So a level 2 predictor predicts intercept variance. An interaction between two level 2 predictors would predict intercept variance. Level 1 predictors should predict residual variance at level 1, either as a main effect or as part of an interaction between two level 1 predictors. What happens in terms of level 1 predictors on the level 2 variance depends on the rest of the model. So if you have a level 1 predictor that still has level 2 variance in it, meaning you've done some sort of constant centering, it's hard to tell what will happen to the level 2 variance. If it's in effect in the same direction that you've omitted, it will likely go down. If it's in the opposite direction, the level 2 variance could go up. If you have group mean centered level 1 predictor, then by explaining the level 1 residual variance, it will actually drive the level 2 intercept variance back up. So don't worry about what happens at the wrong level, I would say. When you are reporting effect sizes, you want to focus on the level that it should have affected. Just make sure your model's not misspecified by smushing and doing so. So now we get to something new. The idea of random slopes. So the term sort of fixed effect is an umbrella term that holds under it the fixed intercept and fixed slopes. And the key idea is that fixed means everybody gets the same, right? Those are, in the equations, they don't have subscripts for P and G or I or anything like that. They are the same, they're constants that are applied to everyone's predicted outcomes. And we talked about random intercepts so far, the idea that each group gets its own mean deviation. And now we're picking up another kind of random effect. So random effect has intercepts and it also has slopes. And in this idea, it's the idea that the effect of an individual level predictor differs across groups. Each group needs their own version of the level 1 slope. That's what that means. So you can have a situation in which you have either, both, or neither of these be true for any level 1 predictor. So just to give you a couple pictures of this, let's say that we have a level 1 x variable on the x-axis and a level 1 y variable on the y-axis, and the heavy black line describes the mean for the sample, and the thinner black lines describe the effect of the level 1 predictor for different groups. And I say, in this one shows a lack of a fixed effect of the level 1 x nor a random effect. So the fixed effect is what happens on average. So far we've said that it's not just on average, it's the effect. Well, that's an assumption. It's the average effect across groups. So if we have a slope that's flat like this, we're saying that having more x than other people in your group doesn't matter. So there's no fixed effect because on average, level 1 x doesn't matter. But it doesn't matter the same for all the groups. And therefore there is no random slope either. All the groups can share the same slope. What happens on average adequately describes what happens to each group with respect to the level 1 predictor's effect. We can also have something like this. Now the level 1 predictor has a positive slope on average, and that slope is equivalently positive for all the other groups. So we would say, yes, there is a fixed slope that we need in the model. On average, the predictor's effect on the x-axis here is not 0, but everybody's slope across groups, every group slope is the same. So it's not random. Everybody can share the same slope. So these pictures describe a model in which the only term that needs to be random across groups is the intercept, the starting point, if you will. You can have a random effect but not a fixed effect. So let's say that we have something like gender differences in the effect of, let's say, gender differences on math across schools, let's say. Are boys better than math than girls or vice versa? So if we have gender on the x-axis here, let's say on average, there's no effect. Boys and girls do equally well. But I tested that level 1 gender effect to see whether it varied randomly across schools, and I find out it does. That would create this type of picture, where in some schools, girls are higher than boys, and other schools, boys are higher than girls. So they may cancel each other out. So the effect of gender requires a different slope across schools. The average slope is insufficient. And you could also have both. So on average, there is an effect of the variable, but the effect of that variable varies across schools. So does each school, does each group, each school, whatever you have, need their own version of the level 1 effect? If so, we need a random effect in the model, a random slope specifically. So to do that, go ahead.
So for the case so if we really know there's no difference between boys and girls,
Mm-hmm.
then how come we are interested in the difference, like the gender difference across the school like this?
Because, so you're talking about this picture, the bottom left?
So if you already know there's no difference between boys and girls, like,
There's no difference on average,
oh, okay.
but that is a misleading thing to say.
Right.
So the reason that there's no difference is because if you aggregate positive slopes with negative slopes,
Mhm.
the average of those is a zero slope. But there may not be any school in the sample in which there is no gender difference.
I see. Mhm.
It's a misleading average. It's similar to how people talk about not interpreting marginal mean effects if you have an interaction. Like what happens on average is a washout of different patterns of some kind. Yeah. So this is why, like, even if you have an effect of a level 1 predictor in a model, when you test the fixed effect, which is what we've done so far, that's not significant, you don't pack up and go home. It's possible that you have this situation where the fixed effect is not significant, but the random effect variance around it, the different slopes around it, are different from each other. It's possible to have either, neither, or both for any level 1 predictor. Okay. Other questions? No? So in terms of equations, as foreshadowed at the end of the last class, it looks like this. So because the example I'm going to show you with random slopes is the one we started last time, free and reduced lunch, because that's a binary variable, I didn't group mean center it, I just left it alone. I entered the group's mean for free and reduced lunch in at level 2. I'm starting with that as the basis of my equation. So we have a level 1 predictor that is still contains both the level 1 and level 2 variation. We have the group mean entered at level 2 to control for the level 2 part of that. So the level 1 effect becomes the within effect, and I have added a new term here. So I have spaced this over so that you can see that we are omitting things here, and to see the parallel. Here's our new friend U1. So this is a new kind of random effect. Previously, we had U0 that went with beta 0. Now we have U1 that goes with beta 1. If I had a beta 2, can you guess what its U would be called? U2. And a beta 3? U3. Yeah, they match. So everything in the beta 1 equation starts with a 1. The second number keeps track of which term it is at level 2. Everything in the beta 0 equation starts with a 0. The second number keeps track of what order of predictor it is in the level 2 equation. So this U1G is a random slope for the effect of x. The fixed effects are interpreted the similarly before, just now we're adding the idea that each group needs a different version of this fixed slope. And so it starts out conceptually as what we had, the same as the empty model. Gamma 1O is the average within slope across groups. U1 is how far off group G's slope is from that. So the mean of the slopes across groups is gamma 1, and then we add to the model a variability for which this would be the value that's expected for each group. So we're adding a variance of the U1s to the model to go with a variance of the U0s. And because each school has 2 random effects now, we allow U0 and U1 to have a covariance in the model as well, because they both relate to the same school. So adding this to an example, just what this would mean conceptually. For example, if we have students, pupils nested in level 2 schools for G for groups, X is the time the parents read to them, and Y is an end of grade reading test, let's say. So note the centering here. Reading at level 1 for each pupil within each group is centered at some constant. Doesn't matter what it is, but people pick ones that are near the middle, such as the grand mean. This group mean reading is centered at another constant. By the way, could I have picked group mean centering for this level 2 reading variable? Would that have been another choice, or would that make no sense? Could I do group mean centering for level 2 reading? It is already at the level of the group, yeah. So this decision as to whether you're using group mean centering or constant centering is for lower level effects only, because you have to have the upper level variable to center it around. A level 2 variable in a level 2 model, you would only have a choice of what's that constant to center at, so that 0 means something. So there's no wrong answer for that one. So in this model, then gamma 0, 0 right here, that's my fixed intercept. That would be the expected test score when level 1 reading is at C1, level 2 reading is at C2. And then gamma 1, 0, that's my within group slope. So it's the difference in your reading for every unit more reading you do than the rest of your school. It's the average within group slope. The level 2 contextual slope, gamma 01, that's the extra effect on your test per 1 unit higher school mean reading after controlling for student reading. And if I want to get the between school effect instead of the contextual school effect, I add within plus contextual, and I get between. Within plus how between differs from within gets you to between. So this one I could ask for as a linear combination. So remember all those lin coms I made you practice? This is why. We need them. And we'll need them for interaction terms too. This is the effect of school mean reading, not controlling for student reading. In terms of the variance side of the model, each of these means something different now with the inclusion of the random slope. So level 2 random intercept is U0G. That is the deviation between the actual intercept for each school and the school mean conditional that is predicted by this model right here. So some schools are predicted to have different mean test scores because of how much reading they do on average. U0 captures whatever is left. So U0G represents the idea that the random intercept variance should be explained. It should be lower than it was before. So this is like U0G left over. For that reason, some people start calling these the level 2 residuals because they're leftover quantities. I'm not going to do that to you because I say level 1 residual, level 2 random effect. In this model, these are random effects whose variance has been partially explained with respect to the intercept. The other thing that changes is that U0 is now conditional on where the level 1 predictor is centered, where 0 is. So the easiest way to explain why this is just to go back to this picture. In the top 2 pictures, parallel lines, right? Intercept is this. People at home, I'm doing my hand up and down to mimic a y-axis, right? This is the shift in the intercept. If you were to look at how different these lines are in the top 2 pictures, you would come to the same conclusion no matter where on X you looked at it because they're parallel. They stay equally spread out because they're parallel lines. That is not true in the bottom 2 pictures. How different the groups are depends on where you are on the x-axis. Because what adding a random slope means is that the differences between the group predicted by the model vary by x. More specifically, they vary as a quadratic function of x. It's actually a parabola shape form where the variance is at a minimum at some point and it expands on either side or away from that. So the intercept variance is specific to wherever 0 is because it's conditional on slopes that vary. So it's not just intercept, it's like intercept at x equals 4 or intercept at group mean centered x, meaning it's 0 for the group. So just keep that in mind that the intercept is conditional now after you add your random slopes. The slope then. Right now this U1G is unconditional. It is all the reasons why the effect of reading more than others in your school varies across schools. Why is reading more helpful in some schools than others? I don't know yet. It's all the variance there is to be had across schools in the student level effect of reading. So once we have U1 and U0 for each school, we pick up a covariance. That is not shown in this version of the equation, but I'll show it in another version in just a little bit. And then last but not least, level 1 residual E is still the deviation for each student from the outcome that is predicted by the model and their real one. The only difference is what predicted by the model means. Now it has an extra variance component in it that's going to borrow some of what used to be residual error. But I wouldn't call this explained though. Because U1 is still an error in and of itself, we don't know why some schools have stronger effects, I hesitate to call that explained variance. Some people would, but I can't wrap my head around it and I refuse to do it. So picture time. I stole this picture because I liked it, so you can see the source on the bottom. So we have random intercepts only on the A picture. That would give a level 2 model for beta 1 that just has a fixed effect in it. So everybody has the same slope. Because the model already had a random intercept, that's why they differ on Y. Versus the B panel picture shows different slopes and different intercepts. The different slopes is created by adding U1 as a random deviation off the fixed slope. So in this picture, the average slope given by the black line is positive. If we look at the red slope, their U would be negative. Not because they're going down, but because they're going up less. Their slope is less positive. So if you start with what it is predicted to be on average, to get to what it is for them, their deviation would be negative. Similarly, the pink slope. Their U deviation would be positive because their pink slope is more positive than the average black slope. So U's are deviations. They're just deviations in slopes.
So is it possible just going down?
It's possible that it could go down. That would be like a really negative U would bring it all the way from positive past neutral past negative. But yeah, it is totally possible. I'm just saying if you see a U that's negative, that doesn't necessarily mean they're going down. It could mean they're going up less. If the fixed slope is negative and the U is negative 2, then they're going down more. That's a more negative. See, more positive, more negative, less negative. It's back. It's the same.
So
Yeah.
in this picture, the U0, like the U0G is the deviation.
Mm-hmm.
If we draw like a vertical line, starting from the solid point?
Yep.
Okay.
Yeah, and that's what they're trying to do is sort of extrapolate. Like if you didn't center, right, so x equals 0 is outside your data.
Oh, okay.
The random intercept is whatever is implied by here. If you have the same slopes, it doesn't matter. Like this difference would be the same here versus here versus here. You go to this picture, how spread out the groups are and their rank order at this point is necessarily going to be different at another point because they cross, which means the rank order shifts. So the correlation between the intercept and the slope depends on where the intercept is. It's not a fixed idea. And yes, here's another picture. So let's say that these are two, this is a blue line is the average, conditional on level 2 reading. Actually, no, the red line is the average, that's right, and the blue line is for one particular school. So this is within, after controlling for level 2 school differences. So the red line given by the fixed effects, the blue line created by adding the random effects. So gamma 0, 0, what's that? Feel free to read from whatever's in front of you. Fixed intercepts, right? Definition? Not grand mean, this ain't empty. Expected outcome when, ... Yeah, when this is C1, so whenever that is 0, right? So in this picture, let's say that I have 4 levels of student rating. The trajectory that's predicted through it by the model says that the end of the line, basically where 0 is, should be about 10. Now their actual score at that, if you conditional on that, if you were to take like a mean, may not be that, but it's where the trajectory is predicted. So the fixed intercept is the expected outcome when the predictors equal 0. So I'm already factoring out the level 2 predictor, just focusing on level 1. Now this particular school, they start out lower. So their U0G, which is how far off their intercept is, would be negative to get them down to where their slope is predicted to start. Not to where, like, if you took the mean of the students who had a 0 would be, but where their slope is predicted to start. So if I have a fixed intercept of what happens on average of 10, and I subtract 4 to get them down, their intercept is going to be 6, yeah. So that's how each school gets their own. So like their beta 0 intercept, after factoring out reading, would be like what happens on average minus how far off you are. So that their own intercept is given by beta 0. Then we have gamma 1O as the level 1 variable. So in this notation, I'm substituting in so that beta 0 is the first term in brackets, beta 1 is the second term in brackets. So gamma 1O is my fixed slope for level 1, right? The expected change in y per unit change in x. So remember this little triangle thing from algebra way back in the day, like rise over run? So this is a slope of 6 that generated that line. Now how about my school? They grow more. Their slope is more positive. So to get them to where their slope is, I give them a U1 that is a positive 2. And so therefore, what must their blue line slope be? 8. Yes. So each school gets its own version of an intercept and its own version of a level 1 predictor. From there, E is how far off for each student their actual outcome is from the one that's predicted for them. Predicted for them now includes different slopes. So like E for each person would be the difference between what they got and what their school's trajectory was. So back in this picture then, like the dots are the people. There's a pink school, there's a green school, and the E's are then how far off they are. And if schools need different slopes, those offnesses should be less after you factor in the different slopes than if you need them all to be the same. That's the logic.
I have a question.
Please.
Could you go to the next slide? Yeah, here. So the U0G is -4. So it's how far off the end of the blue line deviate from the end of blue line.
It's supposed to be like this line to that line.
Yeah.
My little thing is
Yeah.
off. Thank you. Yeah, let me see if I can fix it. Yeah, I have it looks different on different versions of my computers. Let me grow my little thingy here. All right, there, almost. Thanks. Not quite. I'll have to fuss with that later. But yes, thank you. It's the difference between where the lines end up. That's what we're going for here. Yes. Here. Okay. So all in all, what we have in this model are 7 parameters. So 3 fixed effects: intercept, the 2 slopes, within and contextual, or within and contextual, I should say. Model for the variance has 4 parameters. So we have an intercept for each school, which gives us an intercept variance across schools as the parameter. A random slope variance across schools, so those are both tau squares. I use the U's as subscripts to tell you what is the variance of, but these are all random variances at level 2. And because the U0 and the U1 come from the same school, they get a covariance in the model. So that's the tau U01, and then level 1 residual variance, same as always. Yeah.
So I have a question about fixed level 1 slope and the random slope deviation.
Mm-hmm.
So from the equation, it's hard to associate the two into one term if you want to get like 6 plus 2 equals 8.
Mm-hmm.
Because the U is influenced, right? I think there's
This term is one thing, and it multiplies that thing.
Yeah.
So you're saying I have an order of operations problem? Okay, let me fix it. I probably did that because it's going to take me into the next line, and I didn't want that. See if I can make it go up. Come on, you can do it. Oh, shoot, that one. No? Oh, I did it. Okay, thank you. It worked. Oh, it's moved my E over. Darn it. All right. See, then it's like I have to fight with the font. And maybe I can just call it Y. Can we live with that?
Yeah.
There. Yes, thank you for pointing that out. Are the rest of them okay? Okay. Yes. Yeah, this term in parentheses here, this is beta 1. And it multiplies the variable. So yeah, what I probably could have done is just taken this bracket and moved it over, but that works as a thing. We'll keep that. No worries. All right. So I point out the number of parameters because when you think about it, how many variables are actually in this model conceptually? Conceptually, like if I had a research question, it would say, what is the effect of reading to your students on their test scores, right? I have 7 parameters that answer that question. Now I say that because a lot of times people have big data sets that have lots and lots of variables and they want to control for lots of things and look at other things. I have one concept and I've just made 7 predictors out of it, or actually 5 after you control for, or 4 I would say, because there's a fixed intercept no matter what, a random intercept variance no matter what, and a residual variance. So I've got 4 parameters out of, plus 5 if you count the covariance, but never mind. A lot, that's what I'm going with. So these things can get very complicated very quickly. Okay.
And do you have to run the significance test like all the parameters?
Yes.
Residuals?
Say that again?
You have to run the significance. I don't know. It's gonna be t-test, like it's a lot of something test, but you have to run the whole test of significance to the whole parameters.
Yes, what a great segue. Did you look ahead? Did you look ahead at the next set of slides? Because that was like the best segue question I could have ever asked for this. Well done. Yes, you do. But how you do it differs based on whether you're testing a fixed thing or a random thing. Dun dun. So we're talking about comparing nested models, right? How many of these fixed effects do you need relative to a model that doesn't have them? How many of these random slopes do you need relative to letting the slope stay just fixed? So in terms of terminology, by the way, this idea that you have both together, some people would say that I have a random slope because it varies. But how I get a random slope is by combining the fixed slope and the random slope deviation. So if you have a random slope, the fixed slope always stays with it. Because the random slope is what the fixed slope is deviating, the fixed slope is what the random slope is deviating from. So it doesn't make any sense to have a random slope without its fixed part. But people just don't say it that way. Like technically speaking, I could say that there is a fixed slope and a random slope for level 1 predictor in this model. But what I would write in a paper is that it had a random slope, because that implies it had a fixed slope too. So that can be confusing sometimes. But yeah, we're talking nested models. So the things that we've done already, univariate Wald test and multivariate Wald test, right? Each fixed effect has a t that goes with it. Estimate over standard error is t or z depending on whether or not you're using denominator degrees of freedom. And that's univariate. You've learned how to write contrasts or tests to lump parameters together, such as omnibus effects of group or change in R-square, that kind of thing. So any kind of fixed effect, we don't need to do any kind of model comparison. We can ask for significance for the various contributions together or apart. For things that go into the model for the variance, So we saw our first example of this. We had an E-only model, a single level model, and we tested whether or not we needed a random intercept also. We did it via a likelihood ratio test. And I said, we'll talk more about this later. Well, now the time has come for later. So we have to do something different to test whether or not we need any kind of random effect. And that is tested as the difference in -2 log likelihood between nested models. There are p-values that show up on your output in various packages. So you'll have a variance estimate, its standard error, a z, and then a p. You are not allowed to use those p's. Someone will yell at you. There's like 10 people in the world who know the difference in care, and one of those people will yell at you. I can almost guarantee it. The reason is that that p-value comes from the idea of a two-sided sampling distribution. So if you have an estimate, you typically go, 2 standard errors this way and 2 standard errors that way, and you're trying to see if the interval contains 0. Well, what's the smallest that a variance can be? 0. So if you have a number that is an estimate that's very small, that's right next to 0, the standard error can't take it into the negative space. So a two-sided sampling distribution, the Wald test doesn't make sense for that. And it will be less useful the closer it is to 0 when you would need it even more. So those p-values you cannot touch. No, we don't do Wald tests for variance components. We do -2 log likelihood differences instead. The good news is that Stata has a built-in thing to do this called LR test. And so you can get your p-values out of that. And I've written a SAS macro to do the same thing. So you don't have to look up chi-square tables or type things into Excel or do extra things. Type things into Excel would be the next thing I would tell you to do. Chi-dist is a function that will give you the p-value that goes with this thing. Okay, Kayla, did you have a question, or are you just wiggling? Just wiggling? Okay, carry on. Did anyone else have a question? Okay, so we talked about this before, but just to remind you, for fixed effects, what you get depends on how many numerator degrees of freedom, meaning how many things you're testing simultaneously, as well as whether or not you're using denominator degrees of freedom. So Shinji, you asked me this at the time, like if you did Stata regress, is it a T or a Z? It's a T. I learned this in my other class because it automatically uses denominator degrees of freedom. If you run the same regression model using mixed, it is a Z unless you correct it for degrees of freedom. So the default is Z in mixed. And for the exact same model, the default is T in another package. So certain places like M plus doesn't do any kind of denominator degrees of freedom. So everything you get out of there is Z or chi-square. Other programs you have to see, but this is for fixed effects. None of this is relevant for random effects. Just to remind you where the degrees of freedom come from, these are probably 3 different methods that people use to compute denominator degrees of freedom. I tend to use Satterthwaite as my option. That is analogous to the degrees of freedom for a t-test that's dependent between groups that have different variances. It basically takes the information and tries to correct degrees of freedom for how much variance you have at each level, as well as whether the predictor is measured at each level. What tends to happen is that predictors measured at level 2, their degrees of freedom look like level 2. They're based on the number of groups. Predictors that are measured at level 1, their degrees of freedom will look like level 1 if it's fixed, but it jumps to look like level 2 if it's random. And so that's one of the differences. The reason, honestly, that I have this one is because someone way smarter than me a long time ago told me it was a good one to pick, and I nodded and said, okay. But since then, it's because it was the only one that was built into multiple software packages. So I teach workshops. Some people want SPSS. I roll my eyes and say, okay, but they only have Satterthwaite. So to make it comparable across programs, that's the one that I pick. If you're concerned about small samples, there's another one that shows up it's in R, it's in SAS, and it's in Stata. I don't know if it's in other places. It's called Kenward Roger. These are 2 guys that made this up. They use Satterthwaite degrees of freedom, but they also jack with the standard error. They make it a little bit bigger to better approximate small sample variability. And that's shown to work well, but small sample means if you have 5 schools, that kind of small sample. Once you get past 20 groups or so, or 20 total, it doesn't really matter. So just this is why I use those things. I said I'd talk about it someday, and there I have. But no, modeling the variance, testing random effects requires model comparisons. And so this brings up the issue of how you have estimated your model. The differences between these things are coming later in this same set of slides, but there are two different kinds of likelihood estimation that you can pick. There's regular flavor maximum likelihood, and there's residual or restricted maximum likelihood. In this class, so long as we have normally distributed residuals, models for those, which we have right now, we're staying in Rimmel. Once we switch to outcomes that are not normal, like for binary, like logistic models, that kind of stuff, they only come in regular flavor maximum likelihood. If you run these same models in M+, a structural equation modeling package by nature, they only have ML. So this distinction only shows up in one place that I'm aware of if you have normal residuals at all levels of the model. Rimmel is the same thing as least squares if you have complete data. So that's what it is. It only varies if you don't have complete data. So either of these is fine to use. What I'm about to tell you does not matter so long as we're just focusing on the random side of the model, which one you picked. The same procedure is used. The question is, what kind of summary of the model fit does your software get? So log likelihood is the idea of how tall is your model according to the data. It's searching for parameters that maximize the height of your data using a multivariate normal distribution. So likelihood is a positive number. It means tallness, meaning that bigger values are better if you talk about log likelihood. But because you're going to have to multiply the difference between log likelihoods by -2, some software packages try to do you a solid and give the -2 version to you directly, -2 log likelihood instead, which means smaller is better because it's backwards. So this is to say, if you're using a SAS or SPSS mixed, does Elmer give you this? Our people? Or LME? Does it give you -2 log likelihood? Yeah. Like straight up multi-level modeling packages, they give you -2 log likelihood. Stata and M+ are the only ones I think I've come across that give you log likelihood instead. So on your homeworks, the first question I'm going to ask you is, what is -2 log likelihood for your model? If you're going to use Stata, which is fine, just keep in mind that what you get on your output as log likelihood, you have to multiply it by -2 to put it in. If you have the right -2 log likelihood, you know that you have the right terms in your model. So that's why I asked that question first in your homework. Once you get the right terms, if you have the right fixed intercept, then I know you have centered all of those terms correctly. So I will almost always ask for those two pieces of information first as diagnostics. So what we do with these things is take the difference. So the difference in log likelihood, this -2 delta for change, LL, is always the model that has fewer parameters. So for instance, if you only have a fixed slope, minus the -2 log likelihood from the model that has more parameters, for instance, after adding the random slope. That is the direction that it needs to be for the result to be positive. So it's a difference in fit after adding new terms. We then calculate the degrees of freedom for the test, which is the difference in the number of terms that were added. So in this case, for the result to be positive, it's the number of parameters from the bigger model minus the number of parameters from the smaller model. That -2 log likelihood is supposed to be chi-square distributed approximately, given degrees of freedom of the difference in the test. So to get the exact p-values, you can use chi-dist in Excel, as well as Stata LR test or my macro. So in general, the way that you talk about this test in terms of significance is that if you are starting with a reference point of a smaller model, meaning that you have fewer parameters in it, it's simpler, and you add something to make it more complicated. If the difference in -2 log likelihood is significant relative to the cutoff value, you would say that your model fit is better. It's significantly better. So for instance, if I add one term to the model, does anyone have the chi-square distribution memorized at p less than 0.05 for degrees of freedom 1? critical value? You don't have to, by the way. I just do because I'm a nerd. There's only certain numbers that I have room for, but this is one of them. 3 something. 3.84 specifically. So if I add one thing to the model and my -2 log likelihood changes, goes down because smaller is better, by more than 3.84, I would say I have significantly improved model fit. The thing that I added needs to stay. Let's say that my change in -2 log likelihood was only 2. Then I would say that model fit is not significantly better. It got better a little, just not enough to be considered exceptional at p less than 0.05. Let's say that I added 2 parameters. That critical value is 5.99. 3 is 7.82, 4 is 9.49, and 5 is like 11 something, and that's where I stopped memorizing. So the exact p-value will be given to you. You don't have to memorize these values, but you can get used to seeing them and sort of appreciating what they should be. If you go about it the other way, if you're thinking about the comparison as I have this really complicated model, does it really need to be this complicated? Can I take some things off and have it be okay? Then if you take parameters away and the difference in -2 log likelihood is significant, that tells you no, model fit just got worse. You need them. If you take things away and it didn't get worse, then the model fit is not significantly worse, meaning, you could take it or leave it. They didn't really help. Now that may sound strange, but I can guarantee that you guys have seen at least one example of this in your life. Can you think of a situation in a stats class where you would have done the second one? Good luck. You start with what is a more complicated model and you see if you can simplify it and have it not be worse. Does that sound familiar? Backwards something? Backwards selection in regression is analogous, except that it's not model fit you're talking about, it's effect size. Because all regression models that are univariate fit perfectly by definition. I don't know if Kayla, you would have had this yet, so you're excused from this question. But I know some of you others would have. Measurement and variance. So in a factor model context, when you have, you want to know whether or not the measurement model parameters are the same across groups, you start with a model in which they all get to be different, and then you fit a model where they're all the same, and you want to know if it is worse or not worse. How about this even more simple than that? How about the measurement model itself? Have you guys had SEM, confirmatory factor analysis? No, not yet? Okay, you guys can sit there and go, but I'm trying to make connections here, right? What's the saturated model in SEM? Well, let's go CFA. Yeah, you better get this one right, Jihoon. He just gave a poster all about this and basing it up, right? What's the saturated model?
Saturated model is item correlate with each other.
Yeah, it's the item covariance matrix, right? So another way of saying it is that you have as many parameters as you have means, variances, and covariances of the items in your data. And what do you typically then try to do?
Compare your current model with saturated model to, if it's not significant, then the absolute model fit is good. If it's significant, that means your current model is significantly worse than saturated model.
That's right.
So the absolute model fit.
Yeah, so if you fit a one-factor model, for instance, you're trying to see if the factor loadings that are fewer in number than the covariances can do as good a job as the covariances. Worse or not worse. So the whole objective is to have a non-significant chi-square, which means not significantly worse. That comparison, what's known as the chi-square test in SEM, that is a likelihood ratio test. That is what it's doing. So this is just to say, your point of reference is only like how you're thinking about it. So if I add something, I can say that the model is, and it's significant, I can say the model is better. If I think about what would happen if I took that away, then I would think, oh, that would make it worse, so I want to keep it. So I say this because people screw this up in writing all the time. So like they say, I tested a random slope and it made the model worse. No, can't happen. You tested a random slope. If it was not significant, you didn't make the model better. You can't make it worse. Not according to log likelihood.
I have a question. Is there any saturated model in multivariate model level model?
No! Yeah, that's coming. But yeah, so all that stuff I just said about the saturated model, that thing doesn't exist in multi-level modeling land. It would only exist if you had perfectly balanced data in which the same number of people were in each group. Because then only then would you have a single covariance matrix to come back to. Yep.
And just two approach give you the same result. Like when you start from the most simplest model, item parameter, and do the test, and you start from the most complicated model and reduce it. Does it do the direction or guarantee the same?
So long as the models, the set of models to be compared are exactly the same. It's not like a pathway, like where if this is significant, then do that. Like, so long as you're not going down some sort of like thing where you could end up at a different place, yeah, it doesn't matter. It's just how you talk about it.
Okay.
And so like in everything that we're going to do for the most part, it's better, not better. But I'm just saying there are other areas in which it's worse, not worse, is what you want to know. So the other thing that would be relevant to your report is something called information criteria, which is an adjustment of the -2 log likelihood based on the number of parameters. So by these standards, you can make your model worse by adding stuff, because it has to be enough better based on the penalty for the number of parameters you've added, as well as the penalty multiplied by a sample size for BIC. Now, I will point out that nowhere on your homeworks, by the way, will I ask for these things, because I discovered a couple years ago that Stata computes them incorrectly when you use Rimmel. Oops. Every other program in the world uses the number of parameters as the number of parameters in the model for the variance, because in Rimmel, models with different fixed effects are not able to be compared at all. Stata uses the number of fixed effects too. So that is to say, if you use Stata to do these models, it will be internally consistent and fine, because the way that they do it wrong is the same across the board. And these numbers don't have any meaning at all. Like if I told you I had an AIC of 820, you'd be like, what the hell is that? And I'd say, yes, that is correct. What the hell is that? And then if I said, oh, but I did this model and now it's 824, then you should say, keep the first one. 820 is lower wins. So it'd be like, in SAS, it would be like 820, 824, and in Stata, it would be like 818, 822. Like the relative differences will be the same, but the absolute comparison won't match. And so if you're trying to replicate what someone else did in a different software package, you have to take that into account. So just as an aside.
Which one do you trust more, actually, AIC and BIC? If like AIC, like one model like has the lowest like AIC, but another model has like the lowest BIC. Which one do you think?
The one that makes me the happiest. Because yeah, that totally happens. They will disagree with each other. Oh, and by the way, what's n? Log n? Stata does something different than SAS by default on log n, and SPSS does something different than both of them. Because in multi-level model land, what's n? Is it the total sample size? Is it level 2 sample size? It is in SAS. Yeah. So, question?
I have a question.
Oh, I'm supposed to shut up now, aren't I? Yeah. This is one of those days where class just ended and I'm still like talking. So, last question and then we'll adjourn for the day.
Okay, I have a question regarding the ML and the remote, because according to your said is remote use auto parameter, but the remote use the variance auto parameters. My question is, when you try to compare different models, and then which one do you prefer? Because the more parameters you get in, it's more likely to overfit the model. There's a risk. So, do you think it's better always use the remote because it has a fewer number of the parameters, which means that it's more likely to get the result wrong because you won't overfit the model?
No, it's the same model either way. Because the thing is that if you're doing Rimmel, anytime you would do a -2 log likelihood difference, it's only because you've added something random. You've kept the fixed part the same. That's the only way the test is valid. So the fact that it only counts the parameters that you could potentially change doesn't change anything else.
So there's no recommendation for which one we should use?
The recommendation is after this,
So
but
you say complete data, that is a different issue. I mean, just everything.
REML is better for small level 2 samples. That's it. Well, yeah, that's coming, but I gotta stop talking now because class is over. So.
I was confused, like my REML and then.
Yes. Yes, we'll pick this up on Thursday. Ask me that on Thursday because that will be a lovely segue into the next several slides.
Oh, really?
Yeah.
Okay, I'm sorry.
Almost as good as his. The segues are coming. I love it. So, all right. So office hours start now. I will see you guys on Thursday. Let me know if you need anything.